So, in this case this CLC, let us start the program with CLC, which is clear console, clearing all variables. First one is area calculation, area as a function of y, b, m1, b, m1, m2, these values are fixed values for any section. Only varying thing is y, this is dA by dy. Third one, this is r, h or hydraulic radius, and fourth function, this is drh divided by dy. Fifth function, this is c l I n n plus 1. Then comes our function, which is dc or dc by dyi. This is dc by dyi plus 1 I plus 1, and next one is dc by dy q, dc by dq, this is I, and next one is dc by dq I plus 1. So, we have defined C L I without specifying this L I here. I have written this. This is dCLI, yi, dc yi plus 1, dc dqi, dc dqi plus 1. Now, within this again we need to specify this MLI, this is MLI n n plus 1. Next is specification of dm by dy I, this is dm by dy I plus 1. After this calculation, interestingly please note here that we have used this q abs terms here, q abs terms here. These two are q, this is d m by dq I, and this is dm by dq I plus 1. Now, after specifying this, we need to specify the boundary conditions. So, what is this boundary condition function? This is boundary value function, this is boundary condition B and D con, this is type. If type is 1, so we will specify the depth. If type is 2, then we will specify discharge, then junction number, depending on the junction number we can specify, and TV or time value is required in this case. So, type 1 junction number 3, we have 1.43, which is specified flow depth at the end point. Then it is type 2 and junction number 1, this is TV is less than 2000, then this starting from 50, 50 plus 100 divided by 100, because it is ranging from 50 to 150. So, 100 divided by 2000 into TV, this TV is greater than equal to 2000, then 150 minus which is the maximum value, minus 100 divided by 2000 into TV minus 2000, and TV is greater than 4000, then this is fixed value 50 meter cube per second. The same thing is specified for junction number 2, which is again boundary junction. So, with our initial information, let us say this is our G value, APS max, T max, delta T is 250 seconds, and theta is 0.5, psi is 0.5. So, theta equals to 0.5 and psi equals to 0.5, and junction number is 4. Boundary junction, we have 3 boundary junctions, channel number is 3. Now, this is our channel information matrix, junction information matrix, and then we have this junction connectivity matrix. Alpha, for each channel we will consider that alpha is constant and equals to 1. So, this value is 1. Now, we can transfer these values Lx, B, M1, M2, delta x, Nm and S naught from this channel information matrix directly, and M node we can calculate Lx by delta x plus 1, that will give us M node or total number of sections for a particular channel. Now, Z values, we need to calculate these Z values as per our previous calculation thing, that if connectivity, this one junction information, this channel information L9 will give us the starting junction, this is 3, which is giving this junction information is giving the elevation at third column. So, starting elevation is more than the ending elevation, then this factor is negative because we are starting from that section, or this factor is positive if this one is less than the ending or elevation of the end section. So, we need to specify QV, which is Q value at future time level, YV, QV, YO or Y old, Q old, and we have this general identification matrix GID, which we have utilized for our steady state case also. Now, in this case we need to specify initial values. This is 50 and 1.43 for L, and that means channel 1 and 2, and this is 100 and 1.43 for this channel 3. Old time level values, we are taking this as gauge value, we are starting this. Now, we have defined this general variable and we can transfer these values to the general variable. After that, we can start our time loop. This is our time loop, this is our space loop. So, after starting at TV equals to 0 and T count, this is time counter equals to 0, this after entering we can increase this time value TV equals to TV plus delta T, and we can specify our Jacobian matrix A and right hand vector which is R. Time display time in seconds, count equals to 0, RMS equals to 1 to enter into this space loop. After entering into this space loop, RMSE greater than epsilon max, RMSE equals to 0, equation number equals to 0. Then we can start adding equation number when we will be writing the equations for continuity. So, this is for continuity, obviously too many input variables are required for dc dy calculation. So, this is first one, this is second one, this is for yi, qi, y, this is q y I plus 1, qi plus 1, and this is minus CLI. This is for momentum. For momentum, we have this dm by dy, which is for y I, qi, y I plus 1, qi plus 1, this is minus mli. So, after getting this 2 into n1 plus n2 plus n3 number of equations, we should try to get the junction conditions. So, first one is for D condition, which is our condition in this case. Initially 0 if discharge condition 0 equals to 1 if discharge condition is there. That means, if discharge condition is there for boundary nodes, then only we should utilize it, otherwise we should omit it. If in junction information J2, that means column 2, if it is equals to 2, that means our discharge is specified. We should calculate the discharge from boundary condition BND con function, and I will just change this D condition or D con value to 1. If junction number is greater than Bjn, that means boundary junctions, then this R eq and that is equation number, that should be 0, because we do not have inflow condition from somewhere. So, we will have only the variables. So, we should start with the 0 value. Now, if this D con or discharge condition equals to 1, then only we should iterate here. Now, if junction condition or junction connectivity depending on whether it is positive or negative, we can identify the starting and end nodes, and we can add with R eqn equals to R eqn plus q values, or subtract this one qv. For each junction node or internal junction node or boundary junction node, we will have one discharge equation or discharge continuity equation. But if we have flow depth condition specified at the end section of 3, then we do not need any discharge condition there, then we should omit that point. For junction energy condition, if junction information 1, that is first column, equals to 1 somewhere, so then we should specify this boundary condition value directly, and we should directly specify that value into this YV. Now, in this case, if this condition is not satisfied and junction connectivity, this one first column, we have more than one entries, that means let us say for internal junction we have 3 nodes available or 3 channels available, then we should write at least 2 energy conditions for that one. So, that is why I have written L equals to junction connectivity minus 1. that means 1 to 2, that means at least 2 conditions we should add. We have 3 connected channels, so we will have 2 conditions. Now, after writing this, finally what we have to do? We have to calculate this del yq, and we have to add this del yq with gv. gv is general variable in our case. Now, after adding this, we need to update these values, because updated value should be transferred to yv and qv, so that we can utilize this value for next iteration. And we should also calculate this RMSE, because if RMSE is less than epsilon max, we should terminate this one. So, after termination of this space loop, we should update our time loop values, because this new time value will be old time value for our case, for the next iteration, next time loop iteration. So, update value for time n, which is again specifying the value n plus 1 to nth level, and I have stored this value, which is yv at 31, which is equivalent to x is equal to 4000, and I can utilize this value for plotting, so that I can get the desired plot for this one. If you have 100 as del x, then yv and qv should be calculated at 143. If it is del x is 43, then yv and qv should be collected at 283 to get the information about x is equal to 4000. Now, at that point, if I run this one, so time in seconds, so time is increasing. So, after each convergence in the space loop, the time is increasing here. Now, in this case we can see that 2 plots are there. One is for flow depth. So, what flow depth we are getting? Starting from 1.43 here, this flow depth is reaching up to 1.65 and above, but it is below 1.66, and again there is decrease because we have considered one inflow discharge at upstream. So, obviously there will be increase in the depth initially with a lag, this much is the lag, and finally there will be decrease in the depth level, but in this case we can see that some variations are there in depth. We can change theta and psi values to get different values here for depth. In this case, this is a discharge plot, it is starting from 100 because we have specified 100 meter cube in this case. So, this is our plot that we have got. So, interestingly it is reaching up to 165 meter cube per second, and again this discharge values are decreasing here. Initially there is a rise in the discharge, obviously because of inflow condition in the upstream junction nodes at 1 and 2, but finally discharge values are decreasing and again reaching to that 100 meter cube per second value. So, this is all about our unsteady channel flow problem. Now, you can utilize this source code unsteady 1D channel network with reverse CFG1, because we have used only configuration 1 in this case, and try to simulate the same problem with different theta and psi values. In this case, I have utilized theta equals to 0.5 and psi equals to 0.5, but you can change the values of theta and psi and check the stability of the problem. So, obviously, as per literature, this problem, this theta and psi, if I start from 0 to 1, 0 to 1 in this case, if this is my psi and this is theta. So, obviously, this part is unconditionally stable part. That means, if both the values are more than 0.5, then I have unconditionally stable situation, but check what is the solution if I change the values or I decrease one value with respect to another. Thank you.